Welcome back to Quantum Light. In video 1, we built a Hadamard gate on a tabletop with lasers, plates, and a beam splitter. It worked, but it pointed straight at 3 problems. This video fixes them by guiding light instead of shooting it through open air. First, the bench is big, and it only gets worse. Every new qubit needs more space, more mirrors, and more alignment, so a tabletop simply will not scale. Second, there is no real output sensor. We read the bright spots with our eyes. And third, the laser travels dead straight through open air, when what we want is to bend light and merge beams the way copper traces route signals on a circuit board. The fix is a waveguide. Picture a thin channel of high refractive index material, the core, surrounded by lower index cladding. Light launched into the core stays inside and follows the channel, even around gentle bends. Now we can route light into tiny spaces and steer it exactly where we want. What keeps the light trapped is total internal reflection. When a ray inside the dense core meets the boundary at a shallow enough angle, past a certain critical angle, none of it leaks out. It reflects perfectly, again and again, bouncing down the guide with almost no loss. The rule behind it is Snell's law. N1 sine theta 1 equals N2 sine theta 2. Going from the denser core to the lighter cladding, the bending grows until, past the critical angle, there is no escaping ray at all. The light is totally reflected. That critical angle is the arcsine of N2 over N1. Optical fiber is this idea drawn out for kilometers. A glass core inside a glass cladding inside a protective jacket. Its numerical aperture, the square root of n core squared minus n clad squared, sets the cone of light it accepts. Crucially, a fiber delivers that light to one exact spot, so we can finally put a real detector at the end instead of squinting at a wall. And this is cheap. Single-mode fiber costs pennies per meter. Fiber couplers and fiber couple detectors are routine parts. Whole circuits of waveguides can be printed onto a silicon chip in a shared foundry run for a few $1,000s, the same economics that made electronics explode. Now to combine light. Run 2 waveguides side by side. Call the top guide 0 and the bottom guide 1. A photon's path is now its bit. So far, they are independent. A photon in the top stays in the top. Bring the 2 guides close for a short stretch, and something quantum happens. Their light fields overlap and leak across, a directional coupler. Over the coupling length, the photon's amplitude flows between the guides, and the 2 paths interfere. The transfer is exactly a beam splitter. Power through goes as cosine squared of kappa L and across as sine squared. Tune the length so kappa L is 45 degrees and you get a perfect 50-50 split, a Hadamard built right into the chip. So, total internal reflection traps and steers light. Snell's law fixes the critical angle. Fibers and waveguides carry it to an exact detector, and a directional coupler interferes 2 paths. A beam splitter you can print.